Okay, so just before we begin, like an announcement is regarding your next assignments. So one lab assignment and one theory assignment have been posted. So this is lab assignment 4 and theory assignment 4. So the due date for both these is November 26th. So this is going to be your last assignment in the sense of graded assignments. But of course, there are some topics that we'll be doing. So as we go along, I will ask you to try some things out on your own. Maybe if you don't have time now, but maybe something to do for the vacations also. Okay, just some fun things to try. All right, so let's get started. So we were looking at base nets, and we spent quite a lot of lectures talking of various aspects of base nets. So one is inferring independencies or dependencies in the network, and then we looked at deseparation. So that was deseparation. Then we went on to look at inference. So that was variable elimination. And what else did we do? We looked at decision networks. That was the last thing we did, like how you use these inference kind of problems, or how base nets can be used in decision making under uncertainty. Okay, so today what we'll do is we'll look at one more aspect of base nets. I was initially deciding whether or not to do it, but then I thought, base nets are like, very popularly used everywhere. Like almost every machine learning model out there is some sort of a base net, right? For example, like I don't know, have you heard of these latent richly allocation (LDA) or topic models? Have you heard of these?
Yes, ma'am.
Yeah, so maybe not in some course, but you have probably heard of, the buzz about topic models. And basically these are like models where you want to, that they help in primarily in document classification or any tasks related to parsing of documents. But then, its use was expanded to other domains as well. So, somebody was asking me, I think it was Rishabh, what is the use of base nets? Okay, so the way it has been going, probably you won't see the immediate uses of base nets, but stick it from me that most of these models are base nets. For example, what I'm just showing you the Wikipedia page of LDA. So you see the model is this kind of okay, so I think it's a big model, it's a big image, but yeah, the model is this kind of, it's represented using a base net or a graphical model. So there are a couple of random variables. These boxes are like documents. So that if you put boxes when you have like this kind of a structure, if it repeats, so that's when you put. So if there are m documents, there are m such variables, m such random variables, and m documents, and if there are n words in each document, so this also within each document, this gets repeated, the inner box gets repeated. So you don't have to really understand this as of now, but what I'm trying to hint at is, this is actually a base net, and with the words in the document are what are observed. And then you try to make some inference queries, like what is the probability that theta is something given w, and theta is like some kind of a parameter. It's a distribution over topics that you might find in the document. Okay, so such things are like very popularly used, and so this inference problem is a very important one. Okay, and we'll just spend some more time on this topic. So here, what we'll do today is like, yeah, we saw that inference is a hard problem in a base net. So variable elimination, those are all ways in which you do an exact computation of some query probability. Now, if you're okay to have some errors, or if you want to do something like computationally, one way people do is to generate samples from the base net, and then you try to evaluate the query. So just to recollect, your query is something like this. You have a probability of some random variable q given some evidence. Okay, so E1 to Ek. And this is what you want to evaluate, where there are these variables and many more in your base net. Okay, and the way people do is you generate samples of all random variables in your network, and then with those samples you try to compute this probability. Okay, so you just basically do some kind of counting. in all your samples, you look at, the event of your interest, how many times it occurs, divided by, the number of times this E1 to EK, this particular evidence is set. So we will just see some different ways in which you can do it. Okay, so we will just start off with sampling from a distribution, because ultimately, if you want to sample from BaseNet, what you're going to do is generate samples from some distribution. So let's just take a simple example. Suppose you have a distribution over colors. Maybe it's the kind of clothes you have, the colors of your clothes, and maybe something like this. You have red clothes, 0.6 with probability 0.6. So the fraction of red clothes in your wardrobe is 0.6. Maybe green is something like, say, 0.1. And maybe blue is like 0.2. Okay, so suppose you have a distribution given like this. So this is the probability of the color. Okay, and now I want to generate samples. So this is probably something you already saw in your probability class, but let's just recap. So I want to get samples from this distribution, right? And so what it means is, instead of, if I want 100 samples, one thing is, on 100 days, I, wear some clothes, some dress, and then I note down what color I do. Okay, but instead of that, what you can do is, who has the patience to wait for 100 days? You try to just simulate things, use your system, write some code, and draw samples. So at one shot, you get all possible, 100 possible instances of the clothes you wear, of the color of the clothes. Okay, so how do you go about doing this? Right. So what you can do, does anybody remember how you could do this? Did you see this in your probability class? I was told that you probably saw it, but do you remember seeing something like this? Okay, am I audible?
Yes, ma'am.
Yeah. So, yeah, do you remember seeing something of this form, like where you try to draw some samples? It's okay if you've forgotten. You can say you forgot. That's also fine.
Don't remember it, ma'am.
Okay, fine. So, fine, let's just recall that. So what you can do is, okay, so this is a probability is a number between 0 and 1. Okay, so is this correct? This probability is not summing to 1 also, right? So maybe let's make this 0.3. Okay, so these probabilities are all numbers between 0 and 1. Right. So what you can do is, first thing, the way to draw a sample is you first generate something from the uniform distribution. Right. So between 0 and 1, you get a number. Okay. And you don't want any value with more probability. So, all possibilities are equally likely. So you just draw it uniformly from 0, 1. And so what you can have is this U, you want to think of it as a particular probability value, or some way you want to convert U into one of these numbers. So what you do is, if U is less than or equal to 0.6, then I say red. Okay. Now, if U is maybe between 0.6 and say, let me say, make this, it doesn't matter really, but okay, 0.6 and let's say 0.7. Then I say that, I'll think that is a green. I interpret the U as a green. Okay. And finally, if U is greater than 0.7, then I interpret it as a blue. Okay. So this is the way in which, I can, convert a value U between 0, 1 to a sample, red, green, or blue. Okay. So if you look at the ways in which this comes, now this U is generated uniformly between 0 and 1. And so 0.6 of the time you will say it's red. And so this difference here is 0.1. So 0.1 times you will say it's green. So 10% of the time you'll say it's green. And this number, so the possible values here are between 0.7 to 1. So this will be less than or equal to 1 anyway. So then it will say that it's a blue. So in that sense, this is correctly giving you a value from the desired distribution, a sample from your desired distribution, right? So this is a very simple case where there's a fixed distribution, the discrete choices, and you just generate accordingly. Okay, so these ideas also extend to continuous distributions, but we won't look at that for now. Okay, because mostly the ideas are what are important. All right, so just maybe let's just see this in action. So I've just written an implementation of this. So yeah, I just generate a uniform random variable, and I'm just appending this with the samples. So yeah, this is exactly the distribution I told you, 0.6, 0.1, and 0.3. Okay, so I was running something else. Okay, so maybe let me run this, and so I'm just going to draw 10 samples for now, just to show you. Okay, so I'm just running this code. So this is where I initialize the distribution, and this is the function where I'm drawing the samples. And here I'm just counting the samples. Okay, so the number of red, the number of blue, number of green. And then I'm trying to compute from these samples, what is the probability? So number of red samples divided by the total, number of blue by total, and number of green by total. And I'm just trying to see whether it really gives me the probability distribution that I started with. Okay, so let's just see the samples. These are the samples, right? Couple of red, green, blue, and so on. And so if I look at these probabilities, so this is just, we are just validating the law of large numbers. Okay. So here we got this. I mean, here the number of samples was very less, but still somehow it worked. Okay, but it may not always give you, this is too small a number. But sometimes it might not really give you. See, for example, in this case, it was 0.1, 0.7, and 0.2. Right. So, but the thing is, if you have a very large number of samples, this is going to give you the distribution. I mean, this is going to give you the estimates for the distribution you started off with. Okay. So let's see this. So you see this probability red, blue, green. It's kind of in this range. It's close to the true estimates. Okay. So this is a sampling from just any distribution. This is as simple as that. You can just do this. Okay, so now what I'm going to say is I want to sample from a base net. Okay, so maybe let me just pause for a minute. Is this process clear for a simple distribution, how we generate samples? Any questions on this? It's clear? Okay. Yeah, maybe I would just like all of you to type. It's clear? All right. Okay. Okay. So let's move ahead. So suppose now you want to do this more generally for a base net, right? So base net, we have been using this example of this burglary and this alarm network. So what if you want to draw samples from this base net? What does it mean? So what you want to do is basically draw one instantiation. It's like one instance of this network where there is a value of B, there's a value of E, there's a value of A, J, and N. So this is the, this tuple of 5 random variables. That's what you want to generate. Okay. And all these values are as given, plus B, plus E, and, all as given by the network. Okay. Now the question is, now it's not a fixed distribution. I mean, of course, there's an underlying fixed distribution, but what you have is these conditional probability tables. So how do you do this? How can you draw samples from this kind of a network? Okay. So remember, the query that you always wanted to do is maybe something like this. Maybe we'll just use this query. So probability of plus B given plus J plus N. So this is sampling in a base net. And suppose I want to do this. This is the query I want to evaluate. So what's the probability that a burglary happened given John called and given Mary called? Okay. So this is something I want to compute using sampling. Okay. Now, what you could do is you can use these ideas. What you saw about drawing samples from a fixed distribution, you can extend that to the network. And how is that? Because the network has a structure like this. Right. So this was the structure, and there were these conditional probability tables. And what you can do is you can first draw a sample from B. Okay, you can draw a value of B because you have probability of B. Now what you can do is draw a sample from E because you have this probability. And then with these generated values of B and E, you can draw a sample from this distribution A and so on. So essentially what you can do is you can, go through the network, you can visit each node and then use that conditional probability table to draw a sample. Okay, so this is called prior sampling. So this is the most natural approach that you can think of. Okay, so where what the algorithm is like this for each random variable in the base net. So let me call this xi. What you do is you draw a sample from uh, xi, so probability of xi given the parents of xi. Okay? So this we'll call it as small xi. Okay, and you keep doing this, okay, till you have exhausted all the random variables in the network. Now, one particular thing to note here is there's a particular order in which you should do this, right? Because you don't want to do a j at first, or you don't want to do an a probability a. I mean, you want to because you only have a given b and e. So what you want to do is you want to generate the sample for b and e before you generate a. Right. So do you remember there is a name for this kind of an order? Like this is a directed acyclic graph, right? So there's a name for this kind of ordering. Does anybody know the name?
Topological sort order.
Yeah, exactly. So topological. Yes, exactly. So what you do is you follow this topological sort order. So the order is given by this, and so then that gives you a way to draw a sample. So what happens here is the parents of xi are fixed. I mean that you have fixed in previous iteration already. So you use those values. Okay. So maybe let's. I've just coded this up for this alarm network. So maybe we could just see that. And this is actually sampling from exactly the joint distribution. So finally, what you're going to get is a sample like this. So you will get x1 up to xn, right? So this is your sample. And it turns out that this is indeed going to be from the underlying joint distribution, because what you did was you just essentially followed the structure of the base net. And when you do this enough number of times, when you draw a sample from this distribution, it's guaranteed that you are indeed, because of the way you're doing it, you can use, I mean, for doing this step, you can use this approach. And you're guaranteed that indeed you're going to sample from this. And so overall, the joint distribution is, you had this product. So product of xi given parents of xi, right? And this is overall I equal to 1 to n. Right, so this was the joint distribution, and this is indeed going to be the probability of each of these samples. Okay, so that's why this is a correct way to sample it. So let's just see this in action. So I'm just going to do, what I've done here is I've coded the network. So all these probability tables, I've coded it using these dictionaries. And what I'm going to do is I've also implemented the prior sampling. So maybe let me just come in this time taken part. Okay, so prior sampling, what I did is, okay, so I have this already, I've written this function for, generating the simple case, right? For this case where, given you draw samples from the uniform and convert it to that I already wrote it as a routine. Okay, and I'm just invoking that. So what I'm doing is I'm just drawing a sample from B, and then I'm going to E, then A, J, N. I mean, explicitly I've written this because this is a small network, but otherwise you just write a for loop over the entire network structure. Okay, and I'm just going to invoke this. Let's see what it gives. So here, let's start with just 10 samples. Okay, so this is the output it gave. So what's going on here? So let's just see the sample set. So the samples that were generated. So you see, this is there are 10 samples that are generated, and this was the entire set of values. So somehow all these values were minus b, minus e, minus a, minus g, and minus m. Okay. Now what I actually wanted to compute was probability plus b given plus j and plus m. So what would happen is, okay, let me just take an example here, like before I show you things with the code. So the idea behind doing this is I will probably have something like this, plus b, plus e. My samples, if it looks like this, right, maybe something like this, plus b minus e, plus a minus j plus n, plus b minus e minus a, maybe something like this, then minus b minus e minus a plus j plus n. So suppose these, I mean, I'm just taking for simplicity these 4 examples. Now with these samples, I want to compute probability of plus b given plus j plus n. So can you tell me what it's going to be from here? How would I do that?
See the rows with plus j and plus n.
Yes. So basically this one, this and this. So there are 3 rows with plus j and plus n. And so that is
Two of
by
them have
3.
plus b.
Yes, 2 of them have plus b. So this value, as per these samples, it would be 2 by 3. Right? So this is what I would have liked to do with these samples. But what's happening here when I drew the samples, was that, every time I got a minus j minus n. Okay. So so this number I couldn't compute. So how would I do this? Was number of times I got plus b plus j plus n divided by the number of times I saw plus j and plus n, right? So now I didn't see this. This part was 0. In every sample I had something else. So this was not computable. Let's try to increase the number of samples. Maybe that helps. Okay, so again, the number of samples is insufficient. Okay, so here what I've just printed is the number of samples I got for the numerator and denominator. So these are all 0. 100 is not enough. Let's see 1000. So now you see when I ran 1000 times, I got one relevant sample. So one sample had a plus j plus n, and that had a minus b, right? So what I'm going to conclude here is this probability is 0. Okay, so you see that, you see where I'm getting to. You need a lot of samples to do this. And I was just exploring how many samples I actually needed. And it turned out that if I had about 1 lakh samples, I get some kind of a reasonable estimate. And if I do it multiple times, I mean, every time I'm able to see some value here. So let's just run it. Yeah, so here I ran it 1 lakh times. I got 1 lakh samples, and the number of times I got relevant values were 206, a very small number. And so, anyways, here I could compute something. Some 0.24 is the number I got here. But the point is, you need to draw a lot of samples to make any reasonable sense out of the estimates you get. Okay, so that's the issue with prior sampling, but theoretically it's fine. I mean, it is a correct approach to do things. All right. Yeah. So any questions on this or the code or anything? Or the approach, the way in which the algorithm works? I hope it's clear.
Yes, ma'am.
Yes. All right. Okay. So this is the most natural approach you could think of, and that's called prior sampling. Now, you saw the drawback. There were many samples which we just didn't, it didn't give you any relevant samples. So how do you overcome this kind of issue with prior sampling? Okay, so that leads us to what is called rejection sampling, right? And yeah, so the name is it kind of reveals what it is. So what you do is essentially you keep drawing samples. Now you have some evidence, and whenever your samples don't match with the evidence, you just discard it. Okay, so ignore that sample and then repeat the process. Try to get a new sample, hoping that now your evidence will get taken care of in this sample. So it's basically the same algorithm, right? So let me just copy this down. for each random variable in the base net, again, you do it in the topological sort ordering. So instead of, you do this thing, draw a sample from this probability, from this distribution. Now what you do is, if xi if xi is an evidence variable. If xi is an evidence variable, okay, and if xi is not equal to, let me call it as ei. So what you wanted is for the evidence variables, so something like this, right? So probability of query given e1 equal to e1, something like this. So let me just write it as the particular values you're interested in is ei. Okay, so for some I in some evidence set. Okay, so if it's an evidence variable and xi is not equal to ei, just don't do anything. You just discard it. Okay, discard, and then you keep repeating this process. So for how many ever samples you want, for s in number of samples, so if you fix the number of samples you want, s is 0 to maybe number of samples, and so what you get is the new sample xs. This is a vector, is going to be this, right? And you keep doing this. Okay, so I don't know if the algorithm is like fully as per the flow. So maybe let me just show you the algorithm just for the sake of, in the interest of time, right? So this is from the Berkeley slides. So what you do is you keep iterating. So this is n is the number of samples you want, and you sample xi from parents, xi given parents of xi. And if it's not consistent with the evidence, then you just return no sample is generated. And otherwise, you generate this, you go on to the next random variable. So again, I think here n is the number of random variables in the node. So this is for generating one sample. Okay. So is this clear? It's just, you just keep the sample if it matches with your evidence. If it does not, if it doesn't match with your evidence, just throw it. Okay, so just that's the idea behind this. So maybe let me, I think you get the idea, right? Okay, so this is something you can use, and when is it beneficial? If these evidence variables are somewhere in the beginning, right? In your network, you have a large network like this. You have a lot of nodes, okay, and maybe somewhere here there is some evidence. So what you can do is you start off, you reach this point, and then you see a sample which is not matching with what you want to see. Then you can, there's a benefit because you don't have to, go over the remaining part. Okay, you immediately know that your sample is not going to be used, so just discard. Okay, so what I've done now is I've just implemented this. I've just implemented a slightly different variant of it. So where I say that, I want this many samples, and I will continue. I will count it as a sample only if it matches with the evidence. So only if I get a plus j and plus n. So that's the query. Those are the evidence. So only if I got these, I will continue. If it's not, what I'm going to do is I'm just going to repeat running this loop. Okay, rest all remains the same as in prior sampling. Okay, so maybe let's just see how it works. Okay, all right. So okay, so let it both run maybe. So here the number of samples, let me fix it as 1000. Okay, because I'm going to get 1000 samples, whatever it be. There may be some wasted, but I'm going to get 1000. So let's just see what it gets. So prior sampling was done, and now rejection sampling was executed. So the number of relevant samples was 1000 as I gave, because I didn't, whenever I didn't find a plus j and plus m, I discarded it. And keeping all this into account, I ensure that I get 1000 samples. But you see that the number of rejected samples was a huge number. Right, it's about 4,69,000. Right, it's a huge number. To get 1000 samples, I had to discard these many. And finally, the probability estimate I got was 0.28. Okay, and actually for this network, when I computed the values like manually, the value I got was indeed 0.28. I think I had this computation. Yeah, so I computed these values plus b plus j plus m and minus b plus a plus m, and then the value I got was 0.2840. So this way of generating samples actually matches with the value you wanted to get. Okay, but just that you will end up rejecting a lot of samples. Now in this process, you will spend more time. Okay, so let's just see an estimate of both the times. So prior sampling just took this much time, 0.456 seconds, and this took like 1.75 seconds. Okay, so this is a small network, so it's fine, 1 second, 2 seconds, all right. But for larger networks, it's a problem. Okay, all right. So is this clear? Any confusions? Any doubts on this? Okay, you're all very quiet. Jaishika, is this clear? Yeah, great, thanks.
Yes, ma'am.
Okay. Yeah, Prakhar?
Yes, ma'am, it's clear.
It's clear? Okay. All right. So these are simple ideas, right? It's just, it's like very similar things. If you see that something doesn't match what you want, you just throw it. Okay. So now this issue of, a lot of samples being wasted, how do you further overcome that? Right. So that brings me to the next approach, which is called likelihood weighting. Okay. So what it means is what you suggest with likelihood weighting is just don't reject the sample. Once you see that it doesn't match your evidence, you still keep it. Okay. And somehow in the end, you finally, you do some kind of adjustment so that, you don't include these samples really. Okay, so that there's always this feeling, right, that you wasted effort and you just did so much, but then you wasted a lot of things. Okay, so to overcome that kind of that's the principle behind likelihood weighting. So what you do is, in addition to each sample comes with a weight. Okay, so there is a weight for each sample. So there's a weight for each sample. So let me call this ws. Okay, and what you do is, initially you think that, so this is like the weight that you will account for each sample in this computation. So remember here, when we computed in prior sampling or even rejection sampling, the way we computed the query probability was, it was just the count of the number of times you got the relevant sample, right, the relevant data that you got. So what it did is, essentially you were considering the weight of each sample as one. So this is like saying, you count the number of S, where, S with number of samples with plus B plus J plus M. And you treat it as a 1 divided by number of samples with plus J plus M. And yeah, you give it, you treat it as a 1. So this is exactly the same computation. Now what I'm going to do is, in likelihood weighting, instead of this 1, I'm going to take it as some W, okay, some weight for each sample. Now the thing is, by doing that, I will, not have this kind of a condition, number of samples with plus B plus J plus M. So let's just see it a little better. So what you do is, like before, you cycle through the random variables. For each random variable xi in the base net, you do the following. So if xi is not an evidence random variable, what you do is, as usual, you just sample from P of xi. So small xi, that's the sample. You draw it from P of xi given parents of xi. Okay, so you draw a sample from this distribution. Okay, so the symbol, typically if you read textbooks, they will use this to say it's a sample from here. Okay, so if it's not evidence, you just do that. Now, if it is an evidence random variable, if xi is an evidence variable, then what you do is, you set it to be ei itself. Okay, so it was xi. So in the evidence you got, it had to be ei. So what you do is you force this value of xi. So you force xi to take the value ei. Now what you do is you do some adjustment with the weights. So initially you start off with weight for each sample, ws is 1. And what you do at this point is you've done some adjustment here. Instead of exactly sampling, what you've done is you forced this value. So now what you do is you just multiply this with the actual probability of xi equal to ei, given the values of the parents. Okay, so this value of the parents is what you have generated already in your network. Okay, so that's how you do. And you keep going on. And finally, what you do is you cover all the random variables. And what you return is your sample x and the weight. Okay, so this is a vector and this is a number. Okay, so you return these two quantities. And finally, in your query, so to evaluate your query, what you do is you just take sum over all ws, right? So probability of, so let's just write it more formally. So probability of plus b, so let's suppose I'm trying to evaluate this probability. So what this would be is just, summation over all the weights, right? So I hope that's clear, right? Is it clear to you all?
Ma'am, so we calculate the weight for each sample and then take the sum of those weights, right? For each sample.
Yes. Right? Yeah, so
I'm going
it's...
to repeat the previous part once again.
what happened?
No, ma'am, means I want to clearly understood the thing. No? So that's why please repeat the thing.
So this one, the algorithm.
Yes, ma'am.
Yeah. So what you do is, the thing is about, not rejecting samples unnecessarily. You anyway generate the samples, but you just keep a weight for each sample. Okay. So what you do is you keep cycling through the base net, and when you have something, you come across a random variable which is not an evidence variable, then what you do is the regular process. You just generate a sample from this distribution, xi given the parents, okay, and you treat that as an instance of xi random variable. Now, on the other hand, if you have an evidence random variable, if xi is so that comes up in your query like this. So probability of q given xi equal to ei. So something like this. Okay, so this is the evidence random variable. So now when you go through this network, when you hit xi, then what you do is you don't do any sampling, don't generate any new sample. You force this value, right? You just take xi to be equal to ei. You fix this value, okay? But now what you've done is you've not done a sample. You've not actually generated a sample. You should have ideally done this xi given parents of xi. But since you already wanted it to be set to ei, what you do is you just force this. But now what you do is you adjust the weight in this manner, right? So ws, the weight of the sample, now becomes scale it down by this probability. Okay. So what you finally return is this vector. So this is the sample and this number w, right? Is this clear to you all?
Yes, ma'am.
Yeah. Okay, so now, so let's maybe just see this in action, so then things get clear. So what I've done is to actually compute this query. So this is the process where I generate the sample. So this is this likelihood weighting sample, likelihood weight sampling, this procedure. And then finally I compute it using this function. So here what you see is I've also given this weights, okay, as an input. So let's go there. Okay, so I think probably there was a mistake in what I told in just this part, right? The sum. So actually this sum, okay, so let's just, let me just do this again. So this part, right, what you have is the samples and the weights. Now what the sum of, okay, so what does summation ws, right? What does this correspond to, right? So this will correspond to all samples. So weight of all samples. So this is the weight of all samples, and recall that they had plus j and plus m, because now we are forcing this plus j and plus m, right? So because we forced the evidence to take this value plus j or plus m. When we reached j, we said it should take a value plus j, and when we reached m, we said that it should take plus m. So this summation ws is the weights of all the samples. It's the total weight of all samples which are relevant. Okay, but now there's this part also, right? Plus b plus j plus m. So what you do is you just take sum over all samples, and additionally you should with the samples with plus b, samples with plus b alone you take. And now when you have this kind of a conditioning, what you do is you take this in the numerator, and in the denominator you take this. Okay, you take all the samples, the sum over weights of all the samples you consider, and numerator you only look at those which had a plus b. Okay, I'm sorry about this, it goofed up a little bit. Is this idea clear to you? So it's again a ratio of two numbers, but it's just that, the most general case is if you had like every sample was relevant, you generated and all the W's were 1, right? And so then in that case, it will be like prior sampling itself. This number would have all the samples with plus j plus n. So, this is just going to be a count of all with plus j plus n. And this one would have a sum over everything with plus b also. Okay, so this will have plus b plus j and plus m as well. Okay, but there's no need to explicitly say. Okay, is this clear to you? Any confusions in this? So Advait, it's clear. What about the others? Okay, everyone is quiet. Rishabh? Rishabh, you had a question earlier. Is it clarified now? Okay, it's clear. Okay, so let's just see this in action. I'll just run this, maybe the likelihood weight sampling. So here I've just fixed this number as 1 lakh. So these numbers are, basically I ran this many times, and whatever number made sense is what I'm running here. So let's just do this. Okay, so maybe I'll just comment this part out. Okay, and maybe this also. Yeah, so here you see that, I ran it for 1 lakh number of samples. I wanted 1 lakh samples. I got 1 lakh samples. Now what this number is the number of relevant samples in the denominator. So basically this part, right? The denominator for this expression is what I got here and what I'm reporting, and the numerator is what I'm reporting, right? So the sum of the weights corresponding to the relevant quantity that I want. Okay, so that number is like 206. So it's as though you're saying like only 206 of these samples really mattered, because remember all the maximum value of these weights is 1. Okay, so at max 206 were important, and out of that 59 matched with the plus b part. Okay, and so this gave a value of 0.29. But remember, we ran this again a lot of times, about 1 lakh times. So if I ran it slower, so let me see if I ran it 100 times, what happened? So here you see this number, right? So the number of relevant samples. So probably there was maybe about just one sample which was relevant, and it had a weight of 0.05. Right? And here there's nothing at all. So there's not a very robust estimate in that sense. Okay, so you can run this a lot of times to make some sense out of it. Okay, so that's about likelihood weight sampling. So again, we've made some progress in this direction of not wasting a lot of samples. But one thing that goes, that changes here is if you think of it, this evidence is something that you know beforehand. When you're going to do sampling, what is the purpose of sampling. You know that this is a probability you want to get from your samples. Now, until you reach this point, until you reach this evidence variable, you're not going to make use of this, right? So is there something that can be changed there, right? Like right from the beginning, can you make use of this fact that you want to get xi is equal to ei? And so perhaps values of these other random variables might change, right? Because there are some dependencies in the network. So is there something you can do considering this fact? Okay, so that leads us to what is called Gibbs sampling.
Excuse me, ma'am.
Yes.
Ma'am, I'm not able to understand the correctness of the algorithm. Like, why does summing over the weights give us the...
Why this gives the correct value? Yeah. So if you think of it, what's happening here is if you try to look at the probability of each of these samples. So let's maybe just do that. So the probability of, suppose you got a sample like this, x1 to xn, right? And out of these, some of them, maybe it's ei, right? So for some random variables are going to take the value ei and it's forced. So maybe let's divide it into two parts. So this one part, maybe it has the non-evidence part. So maybe let's call it something like n. Okay, n we've already used. So maybe let me call this z. And there's one part which has the evidence. So let me just write it more properly. So x1 to xn is there. So this is a sample. And out of this, there is, let's just take it as z1 to zk. So this is the non-evidence part. So non-evidence part of this sample. And there is another part which is E. Okay, so this is Z. And E, this is maybe something like E1 to En. Okay, so of course, K plus M should be equal to N. Okay, so that's the way I'm writing this out. So there's a set of two random variables. Let's call it Z and E. Okay, so two parts for this sample. So now what we are saying is what is the probability of this sample being generated. Okay, so what is going to happen is for these parts, for the Z's, what you have is it is exactly going to be probability of Zi given parents of Zi, right? So for I equals 1 to k. So this is for all the Z's alone I'm doing it. If I do that, this is what it's going to get, what you're going to get. Okay, is this part okay, Advait?
Yes, ma'am.
So this part is okay, right? Because we are just doing the same thing for the non-evidence part. Now what you do is if you multiply this with WS, what's going to happen is you're going to multiply this with these probabilities, right? P of xi given the parents of xi. So P of ei given parents of this random variable. So parents of, let's say, xi. So suppose this was xi, okay, a variable xi. So it's parents of this random variable, and this you're going to take over all these e's for this part. So e1 to en, right? So when you multiply with the weights, what you're going to get is the desired probability. Okay, so that's why when you take when you take this ratio, then things become similar. So what happens is the samples that you got, like for several number of instances, this is going to give you a sample. Now you take that sample, but you have this part as the weights. So when you take this kind of a joint product, then the overall expression kind of evens out, right? Advait, is it fine?
Yes, ma'am. I'll go through it once again later.
Yeah. So I know it's at a very high level that I'm giving you the proof. It's not like a case where I analyze the limits and all that. I'm not doing that. It's just to give you a flavor of why it's correct. Okay. When you just do a weight over these samples, when you multiply it with the weight, the overall estimate that you get will be fine. It's just finally your samples that you draw are not exactly from the correct distribution, but the final query, when you do it, you account for this difference in what you generated and what you wanted. So more generally, this kind of an approach, it also comes under the framework of what is called as importance sampling. So many times what happens is, you don't really know how to draw a sample from a distribution of your choice, but then you draw it from some other distribution, and then you try to do this kind of, it's an adjustment in some way. Okay. Any other questions? Okay, we've all been very quiet. What's going on? Kushbu, is this all clear? Are there any confusions?
Yes, ma'am, it's clear.
It's clear. All right. So the final final sampling method I wanted to talk to you was about Gibbs sampling, but I guess we are running short of time. So maybe I'll show you that in the next class, and I'll also show you the demo there. All right. So okay. So we'll stop here for today. I'll hang back if there are any questions. If not, thanks everyone.